Okay, so thank you, Ivan, and thank you everyone for inviting me to the workshop. My name is Saptarshi Debroy. I'm an assistant professor at the Hunter College and the Graduate Center of City University of New York. I am the founder and director of Disarm Lab at CUNY. So this project is about, or this rather, this presentation is about mobile edge resource management for future smart disaster response, challenges and directions. So this is a rather new project undertaking. So my training has been in cloud and wireless, dynamic spectrum access to be precise. And so mobile edge, I kind of found mobile edge to be the sweet spot between the two. Uh, and then I started to interact with some people from the technology team at Fire Department of New York. So this presentation is more about what my understanding of the kind of problems they're facing for future and what we are doing at our side to solve some of those problems. This project has recently been funded by NSF Early Career Award. So a smart disaster response is mostly has been cloud-based so far. So this is the like a typical architecture of a cloud-based smart disaster response would work. And this is something that FDNY is currently using, or some variation of this. So you have the ground first responders and you have the end user devices, which they connect to the mobile infrastructure, which then connect to the internet backbone and back to the cloud. It can be public cloud or some private cloud that FDNY are running on their own. So the problem is if you are planning to run some application at the device side, you're looking at end-to-end delay of less than 1 millisecond, which is good, but the devices are constrained with power and computation, so it might not be the best option. So the alternate approach might be to run it at the network edge, but if you do that, you're still looking at say 10 to 40 milliseconds, which is not real time, and in some cases, or in most cases, for disaster response, you need something which is actually real time, so close to 1 to 5 milliseconds. So network edge might not be the solution. And finally, if you go to cloud data center, you can run a lot of AI and ML jobs over there, things that are required for modern disaster response applications, but the problem is too far and too slow. So the challenge has been that how to provide near cloud scale resources for mission critical and real-time applications on premise. So something which will give you the computation and energy resources that you require, but very, very close to the site, not even at the network edge, even closer. So the solution that we are proposing and has been proposed by some other researchers as well, which is a fog-based or mobile edge cloud-based disaster response. So this is kind of the conceptual diagram of something that would enable that, where you have the multi-utility vehicles which are working simultaneously as your mobile base stations, and also they have CPUs or GPUs which can run heavy workloads. So in that kind of a scenario, what you can do is you can bring the computation closer, but then it also has some issues because this is not network edge. Definitely this is not cloud. So the problem is, what are the situation, like what are the realities of such a situation? So you have heterogeneous applications. So you have very inexpensive devices. So you're not looking at very high-end devices with a lot of computation. So it's very inexpensive devices because you're dealing with state government money essentially. And you have multiple agencies, a lot of applications running. You have the fire department or the police department, and then sometimes FEMA comes into picture. So you have a lot of chaotic situation happening. So heterogeneous applications with different types of devices and inexpensive devices. And then you have heterogeneous requirements based on what kind of application is running. If you have object detection, post detection, you have some kind of requirement. If you have 3D reconstruction, which is a little more heavy duty, the definition of real time kind of changes in such scenarios. So those are heterogeneous requirements. Environment is very dynamic. You have frequent fluctuations because multiple agencies involved. You might have scenarios where your infrastructure is down, it is trying to come up. You have like a temporary infrastructure which is giving you some sort of energy and network connectivity. And then you have resource availability, which is fluctuating as well. And then on top of everything, you have computation energy constraints at the server side as well, because we're running these devices on maybe multi-utility vehicles. So these are not really always connected to energy sources. So theoretically, this problem becomes challenging, because even at the server side, you have to consider the energy constraint of the server, which traditionally is not how we look at these problems. So now we'll talk about a little bit of a couple of applications that we have worked with. So first application is object or post detection. I see that my next talk is dedicated to object detection, so I'll keep it short. So object detection is typically used by first responders to figure out whether there are human beings or pets or something like that is stuck in an indoor environment, and to plan rescue operations. Post detection is used for large scale triage, like figuring out somebody who is more needs immediate attention, or somebody who does not require that. So typically in these situations, you have like sporadic tasks happening, and which are represented typically at the director assigned graph. And these jobs have very strict processing and latency requirement, because they're mission critical and you need a lot of high reliability as well. So in these cases, I think we have already discussed that mobile devices have energy and computation constraints. So the default mode is offload everything to the edge. Okay, you have some data stream coming in, you have run some object detection algorithm, offload everything to the edge. That will solve the problem. But what we have seen in our initial experiment is sometimes the transmission delay or transmission power consumption for those large data sets is so high that it makes more sense to run some of the stages of those complicated DAGs locally, so that the intermediate data size is much less. So in this example, it's a very simplistic example. So we implemented it on an Apache Storm, and for heterogeneous computation jobs, we see like the first stages are here. It's very simplistic, just compression jobs. And we've seen that for applications where we are not doing the compression, the transmission is pretty high, and for that the energy consumption is also very high. So sometimes it makes more sense to do the compression locally, although it takes a little bit of energy, but it drastically reduces the energy required for transmission. Because in a critical scenario where you need high reliability and you're working with devices, limited devices, inexpensive devices with limited energy, everything that we can do on the system, which can save or extend the lifetime of the application for even 5 minutes or 10 minutes will be useful. So in these kind of scenarios, doing local computation, again, it has to be intelligent. You cannot just do any local computation, kind of helps. So that has been our observation. So for this application, what we did was we came up with a combination of centralized resource allocation and distributed strategy making using a game to kind of optimize the energy both from the system's point of view and also from the device's point of view. So essentially, we are looking at full versus partial offloading trade-off. So in some scenarios, based on the situational awareness, we will do full offloading to the server. But in some scenarios, for some applications, based on what are the different parameters and what are the resource availability of the system, we'll do partial offloading, which enables instruction level parallelism and can drastically reduce the overall energy consumption of the system. So essentially, the resource allocation will have channel allocation, computation resource allocation, and edge server selection as well. So this is pretty much the object detection. This is already in submission, so I'm not really comfortable to share a lot of results because it's under submission right now. I want to spend a little more time on a new problem that we are looking at, and I think this is where kind of our ideas of involving Cosmos and doing things in the wild experiments comes into play. So this is for 3D reconstruction with mobile edge computing, which might be used and which will be used by first responder for reconnaissance and to plan rescue mission in indoor environment especially. So pick two pictures on the left hand side show examples of 3D reconstruction with high resolution and low resolution. So essentially, the idea is you estimate the position, orientation, and focal length of the multiple cameras that you have in play, and then you figure out, or you reconstruct a 3D scene. The problem with that is it is much computationally complex than object detection or object recognition. And that context, it is very difficult to define what real time is, because in this case, real time might be very difficult to achieve. Less than 1 to 5 milliseconds might be very difficult to achieve. So you have feature detection, and then you have pairwise matching, and then you kind of establish a correlationship, and then you go make it run through structure for motion, which is incremental in nature. And the complexity of 3D reconstruction application increase with moving cameras, moving objects, and modality of the data. So if you have a depth sensor, you have RGB sensor, regular cameras, based on different modalities, the complexity increases. So again, this is like typically the idea of 3D reconstruction. So essentially you have multiple cameras. So, and both the cameras have some translational and rotational relationship. And from there you create a fundamental matrix. And this is what it is called epipolar constant, which is if the object is not moving, this is the constant that always holds. But if you have a moving object, a moving point, and moving camera, then this epipolar constant doesn't hold. And then the application becomes difficult to, or rather the computation becomes much more complex, which requires more computation resources and energy. So for a moving scene and moving camera and multiple camera scenario, you have different camera positions, you have different image positions, and different fundamental matrices, making the problem, the complexity of problem much higher. So this is an example of an original video frame. So you see there are some cars which are moving. Again, the video doesn't work for some reason because the coding is not compatible. So I apologize for that. So we'll have to deal with just the image. So here you have a moving camera. So the detection result using OpenMVG detection is, so these red parts are the objects which are moving. So which the algorithm defines them as moving, but you can see there are a lot of errors because it's erroneous results because of the moving camera and the perspective change. It assumes that these red areas are also moving. So that becomes, so it's a difficult problem to solve, and that to doing it in real time is even more challenging. So that was like the complexity of the problem, but let's see what are the time issues, the time complexity of the problem. Most multi-view stereo algorithms like OpenMVS and OpenMVG are not ideal for real-time processing because they take up a lot of computation time. So this is an example of OpenMVS processing times in seconds. So for very high resolution, we'll see these are different stages actually. Some stages can be done pretty quickly, but densification of point cloud, that takes 54 seconds. Refining the mesh takes 62 seconds for very high resolution. For relatively low resolution, it still takes 28 seconds and 6 seconds for these two stages. So we are looking at not even real time. I mean, it's very, so we are very far from making it real time. And the algorithms are not designed for exploiting parallelism. So if you run it on GPU, it does not improve that much. And if you make the resolution very low, then it degrades the reconstruction quality, and it defeats the entire purpose of doing the reconstruction and designing a mission based on the reconstruction. So what we are proposing is some optimizations from application side and some optimizations from the system side as well. So essentially what we are doing is which is used for object recognition or moving object recognition community, which is background subtraction. So you're decoupling foreground from background, and then moving and feeding the foreground information only to OpenMVS. Hopefully the number of feature points of the foreground is much less than that of the background. And then at some point we can do update and merge, where we are merging the background and foreground information. And this saves a lot of computation time, because what we can do is we can do instruction level parallelism. So we can run the background subtraction part on one server, and the orange part here, which is the foreground part, which goes through the entire set of computation on some other server, and we can achieve instruction level parallelism. And at the same time, for computations which takes a lot of time, so what we can do is we can achieve some data level parallelism for those applications or for those computation parts. So this is something that we might want to offload to Cosmos, because to achieve this at a lab setting, the kind of test bed we have in the lab might be difficult to do. But again, even if we are able to do it, we have to see how it actually works on a real system. So maybe we can emulate an environment within Cosmos, an instance which will kind of mimic what will happen in a disaster setting, and we can offload this entire experiment over there. So this is something I think Cosmos will be very handy to achieve. And then finally, we have another idea. Again, this is just an idea phase. And this is something that we are just started to explore, which is unlicensed disaster response, mobile edge computing, where the future smart disaster response will be opportunistically used unlicensed spectrum in a secondary environment for device to edge data transmission and edge to device as well. So and that can be a realistic premise for 6 gigahertz or even terahertz communication. So the question over there will be how spatiotemporal uncertainty of spectrum impacts the real-time mission critical application. So we have to do certain experiments to see how that impacts it. And then if you are adding, so something that was discussed in the morning session by some researchers is using federated learning for channel availability prediction. So using some machine learning algorithm and federated learning to do it. So if you want to add that into the, put that into the mixture for say mission critical disaster applications. So you have sensing, you have reporting, you have learning, you have decision making tasks on top of data transmission computation. So we are adding more and more tasks and actions to be carried out by the devices, constrained devices, inexpensive and constrained devices. So that opens up a new can of worms. So we need to do some experiments on that, and that is something that I think we can explore and might be something that will be helpful for first responders and those agencies. So these are the questions. I think these are research questions on top of implementation question, experimental questions. So these are something that we can really do at Cosmos. So I think this is where Cosmos can be very useful as a city scale testbed. So that's pretty much concludes my discussion. Thank you for your attention. If you have questions, I'll be happy to answer. And I acknowledge the contributions of my PhD students and the FDNY team and my collaborators at Temple and Samsung Research. Thank you so much.
Thank you, Saptarshi. So we have one question. I'm not sure if you can see in Q&A while Zoran gets ready to go.
Yes, it is a question about how to synchronize the data. So that is really, really important, and synchronization of data for some applications is more important than other applications, and that adds to the complexity of the problem. So yeah, so this is something that we find really challenging, and this is something that we are looking into. Yeah, so this is not by no means this is a solved problem.